Hello, folks. The purpose of this video is really just to help you um, have a file to look at in case you want to review for the exam that we're having Friday. The um, video I'm doing is strictly optional. It's like all of the other information that I posted for you on D2L. You may use it if you wish to. You may ignore it if you wish to do that. That's okay. But I thought I would go over the practice exam with you and fill in any blanks that we need to, and maybe help you decide what relationships are needed for each problem. So with that in mind, let's look at the copy of exam one. That should be on your screen now. The first question has to do with um, the cubic crystals that we've talked about. This particular problem is talking about a face-centered cubic crystal. So let's pull up stop sharing for just a second while I set the other camera up. Okay. Now, okay, now the let's see, how can I do this? Okay, the first question has to do with a face-centered cubic crystal. So let's take a look at what face-centered cubic crystals look like. I'm not going to draw the rest of the cube because all we're really interested in this one is the face. Now, the face-centered cubic has one particle right in the center of the face, and then it has other particles at each of the corners. If you recall, all of the crystals have a corner particle, but in this case, we also have one along the face. So it's asking, what is the diameter? What is the diameter of the lithium atom that forms in this face-centered cubic? So let's pause the share and go back to this one. Now, this face particle, the atoms touch each other right along that direction. The edge length is L, and if you think of this little right triangle, this side is L, and this side is L, and this side is the square root of 2L by Pythagorean's theorem. So if you look across this diagonal, there's actually 4 radii. From here to here is 1, from here to the center of the face is 1, from the center of the face to the edge is 1, and from the edge of this one to the corner is 1. So the square root of 2L is going to be equal to 4R. And since it takes 2R to make the diameter, that would be 2 times 2R, which is the diameter. So the diameter of the atom is the square root of 2. So if I solve for the diameter, it's equal to the square root of 2L divided by 2. So I can put those numbers in, and I should be able to work the problem. I need to go back and take a look at the problem for a moment. And it said the edge length is 351. So this value of L is 351 picometers. Now, since the answer is given in picometers, I can do this solution. So the diameter is going to be the square root of 2 times 351 divided by 2. So I can solve for the diameter of the atom. And the diameter, then we can do the math on that. And we take the square root of 2 as a second function. Square root of 2 times 351 and divided by 2. So we get 248.19. So 248 picometers is going to be the answer to this problem. So let's go back and see if we got it right. And 248 is D, and that is marked as the correct answer. Now, let's think about this problem before we go on to the next one, because I'm certainly not going to ask you that one on Friday's exam. So what would we do then? We would look at the, I better double check and be sure the sound is on this. So let's stop and let's look at, okay, it says that we are okay. But now let's think about the way this problem could have been asked. There are several different, we could have had a simple cubic crystal. The simple cubic crystal, we can also just look at a face if we want to, because the particles touch across the edges like this. So this is L, and if I'm looking at this, there's one radius from here to here and another radius from here to here. So L is equal to 2R, and 2R would be equal to the diameter, so L would be equal to the diameter, and we wouldn't have any math to do. It would just be 351 picometers. Okay, so simple cubic would have been a lot easier. If it had been a body-centered cubic, now this one gets to be a little bit more difficult to do, but actually the equations are not that different. It's just going to change one of the numbers essentially. Now, essentially what happens is you've got a particle on this corner, and we're going down to this one down at the bottom on the back. There's another particle in the middle and another one down here. These are the ones that touch. And if I draw this side here, now this is L, and this is L, and this distance back here is L. So this angle right here is going to be square root of 2L, is going to be the length of the diagonal across the cube. And then the other part of the triangle, so that's going to be this part across the cube. And then there is this part up here that is L. And now this is the part we want going down through here. And that's going to be 2L squared plus L squared, then take the square root. So this side's going to be the square root of 3L. So in the case of the body-centered cubic, the square root of 3L is equal to 4R. And again, that would be 2 times the diameter. So in the body-centered cubic, it's not much different than that one. The diameter is just going to be the square root of 3L over 4R, or twice, well, divided by 2 here. To get square root of 3L over 2 is going to be the diameter of the atom if we're doing the body-centered cubic. So those are the 3 types of, you can have the face-centered cubic, which is the one we did. You can have the simple cubic or the body-centered cubic. The only difference between the face-centered and the body-centered is this one has square root of 2, and this one has square root of 3. So that's the only difference in them. Now, there are other pieces of information about this that wasn't required in this problem, but you should remember. If I've got a face-centered cubic, go back up here, the face-centered cubic would have how many particles? Well, it's got 1/8 times 8 for the corners. So it's got 1/8 in each cell, and there's 8 corners. And then we have to add to that the contributions to the face particles. Half is in this cell and half is in the other cell. So it's going to be 1/2 of the number of faces. And so there's a front face and a back face, a top face and a bottom face, a right face and a left face. So there's 6 faces. So that's going to be 3. So 3 plus the one we have up here is 4. So the number of particles in a face-centered cubic crystal is 4. The simple cubic is simple as well. The simple cubic crystal, the number of particles is just 1/8 times 8. There's 8 corners and 1/8 in each cell. So the face-centered crystal only has 1 particle per unit cell. The body-centered cubic, if we look at this one, it's got the 1 from the faces. So it's 1/8 times 8. Plus the 1 that's in the middle only is in this cell, plus 1. So that's 1 plus 1 is 2. So that sort of summarizes everything that we could talk about, except for density. And then remember, the density is just going to be the mass. So if I have to do a density problem, density is going to be the mass in the unit cell divided by the volume of the unit cell. And that's going to be fairly simple. It's going to be the number of atoms in the unit cell, either 1 or 2 or 4, depending on which kind you have, times the atomic weight, and then divided by Avogadro's number, 6.02 times 10^23. Now that gives you the mass, and all you take for the volume is length times width times height is L cubed. Now, this is the relationship we need. I mean, density is mass over volume. You get the number of atoms times the atomic weight divided by Avogadro's number. That's going to give you the mass in grams. The edge length is often given in picometers, but that's no big deal. In this one, for example, when we had 351 picometers. So if I want to change that to meters, all I do is replace that pico with what it's equal to. So it's 351 times 10 minus 12 meters. And then if I want to convert from meters to centimeters, centi is 10 to the minus 2, so I need a 10 to the minus 2 down here. And then this would give me L in centimeters. And if I want the volume, I have to cube that. So now that would put all of your data in correct units to give you density in grams per cubic centimeter. So this is really everything that we could do related to number one. It wouldn't necessarily be, it would be one of those types of problems, and really it could be any one of them. Now let's look at the next one and see what we would be doing in working problem of this type. Okay. The problem is the normal boiling point of CH3CH2OH is 78 degrees Celsius and heat of vaporization is 42 kilojoules per mole. Estimate the vapor pressure of ethanol at 25 degrees. Okay, so now this one is that relationship we had with vapor pressure, and you have to memorize these things. It's log P2 over P1 is equal to minus delta H over R times 1 over T2 minus 1 over T1. And the normal boiling point, T boiling point, is 78 degrees Celsius, and the delta H of vaporization is given as 42.0 kilojoules per mole. Now let's stop the share and look at the paper a little bit better. So there is the relationship we need. And we were asked to estimate the vapor pressure. I'm sorry, I should have thought about that and wrote it down. We're asked to calculate the vapor pressure we want to know what it is at 25 degrees Celsius. Okay, now we got everything we need. Okay, now, so this really is just a matter of plugging the data in the equation with the appropriate units and make sure that we take our units into account. Now, you can see since pressure is in a ratio, it really doesn't matter whether this is in atmospheres or torr. It doesn't really matter because whatever unit P1 has, P2 has the same unit. So it will be the same unit and they'll cancel out. So what we're going to do then is note that at the normal boiling point, we're going to make this my T2, the higher one, and this is going to be my T1, and the pressure is going to be, well, since the problem gave the pressure in torr, I'm going to do it also in torr. So the P2, the high temperature pressure, is 1 atmosphere, which is 760 torr. So now all we have to do is plug in the data and solve. Now, since I'm solving for something in this ratio, I'm just going to do it this way. I'm going to say the ln of x, and then X is going to be equal to P2 over P1. And P2 is the 760 torr. Okay, so I'm going to solve for that. That's equal minus. Now, think ahead. The value of R is 8.314 joules. And it's joules per mole per degree. So since that is in joules, then I've got to put delta H also in joules, and that's easy enough. I'm just going to write 42.0 times 10 to the third. Okay, now that's in joules. And the R is 8.314 joules per mole per Kelvin. And now I'm going to put in my temperature. It's 1 over T2, and T2 was 78 plus 273 minus 1 divided by T1 is the temperature we're trying to get to. That's going to be 25 plus 273. Now the rest of this is just simple math. So let's, I will do the calculation, and so let's clear this out. And what we're doing is I'm going to work out the parentheses first. So I'm going to say 1 divided by left parenthesis. It's 78 plus 273.15. I'll put it in. And so it's 1 divided by 273.15 minus 1 divided by, again, a left parenthesis, 25 plus 273.15, close. Now it looks like I've got the data in the parenthesis correctly set up. So I'm coming out with minus 5.06 times 10 to the fourth, negative 4. And now I have to multiply that by 42 times 10, negative 42. So I want to multiply that by minus 42 second exponent. Where is it? Oh, I don't have to do the second thing on this one. Let's back that up. I'm going to delete that. This calculator has the exponent here. Exponent times minus 42 exponent 3. And I want to divide that by 8.314. Now, if I haven't really messed some things up, I have now the log of x. The ln of x, I got to be 2.557. So there we go. And now x is going to be e to that power. Those are the digits there. So all I got to do now is find my e function on this calculator. Okay, so it's second e to the second answer. All right. I see something there that looks kind of funny. Okay, so x is P2. Looks like I'm coming out with 12.90. And that's equal to P2 is 760 torr divided by P1. So P1, or P at 25 degrees C, we think that's going to be 760 divided by the 12.90. So let's see, I'm just going to have to type that number back in because something went funny there. So I want 760 clear. 760. Well, I'm having some trouble getting delete. 760 divided by 12.90, and I'm coming with 58.9. That'd be remarkable if that's correct, because my calculator did something funny in the middle of it. What did I say? 58.9. Well, that's pretty good. That's what I got because I didn't carry the rest of the digits. The correct answer is showing 58.8. So this particular problem, there's not much of a way that you can ask this. This is about the hardest way you could ask it. I guess you could give the two pressures and the two temperatures, solve for the heat of vaporization. You could do that. And that's just about it. There's not many ways that this problem could be done other than the one that is shown on your exam. Okay, let's go to the next one, and let's see what we're doing. The normal boiling point of ethanol is 78, and its heat of vaporization is 42 kilojoules. Estimate the energy required to vaporize 500 grams. Maybe I'll try working this on the bottom of the page here. 3. I want the E to vaporize 500 grams of ethanol if the delta H of vaporization is equal to 42.0 kilojoules per mole. Well, if I'm looking at this, I can see if I knew how many moles, I could use that to do the conversion. So the only thing I need to do is take 500 and grams. I need to divide it by the molecular weight. Molecular weight that's given is 46.07 and grams per mole. So this is going to be the number of moles. So the energy to vaporize the sample, let's stop the share so you can see the screen a little bigger, is going to just be equal to 500 divided by 40.07, and that's going to be moles. And then I'm going to multiply that by 42.0 times 10 to the third. Well, let's look at the answer. Is the answer in kilojoules or is it in, it's in kilojoules, so I don't need to convert. So let's go back and yeah. So I don't need to convert. That'll just be kilojoules per mole. The moles are going to cancel, so all I have to do is 500 times 42 divided by 40.07, and that should give me, looks like 524.08, and that would be kilojoules. Okay, let's see if we got it right. Okay, 520. Oh, well, I'm seeing a little bit of a problem here. Let me look at it again. Maybe I put the numbers in wrong. So it's, yeah, I did. 500 divided by 46.07 and then multiplied by 42. Okay, now I entered in the calculator wrong, but this is 46.07 instead of 40.07. That's the trouble with trying to write with these markers. But the answer does come out to be 455.8 kilojoules. And that is answer C, 456. Okay, so let's hurry right along. Okay, we're ready for number 4. And number 4 says, determine the molecular shape of carbonate ion, CO3, 2 minus, carbon dioxide, CO2, and predict whether they're polar or not. Okay, so let's are either of these polar? Okay, well, carbon is in group 4. It has 4 valence electrons. Oxygen is in group 6, and there's 3 of them. And there's 2 extra electrons. So I've got 18, 20, 24. So there's 24 valence electrons in this molecule. Now, the way we determine the electronic shape is divide by 8. That gives us the number of octets. That's going to be 3. And 24 with the remainder 0. We divide the remainder by 2 and we get 0. So the VSEPR notation for this one is AX3. AX3 is trigonal planar. So we've got carbon, we've got oxygen, we've got oxygen, we've got oxygen. We're going to have resonance structures possible. When we put in all of the electrons, we will get this as one of the resonance structures. And it has the same things attached, so it's not going to be polar. Now, we could have known that right here, because if you get AXN, is not polar, no matter what. Doesn't matter what it is. If there are no lone pairs, it's not polar. Now, that doesn't mean everything with lone pairs is polar. But if it doesn't have lone pairs, it definitely is not polar. So this one is not polar. What about CO2? Well, 4 plus 2 times 6, 12, and 4 is 16. So if I take 16, divide by 2, divide by 8, I get 2. And then 16, remainder is 0. 0 divided by 2 is 0. So CO2 is an AX2 type, and it's not polar either. So neither of the two are polar. That should help us answer the question. Both carbonate and carbon dioxide are polar? No. Carbonate, that should be carbonate, ATE ion is polar, but carbon dioxide is not. No. Neither carbonate ion nor carbon dioxide is polar. That's correct. Okay, so we're good with that one. Now, Number 5 has to do with phase diagrams. And again, how could I change that? Well, it wouldn't matter. Whatever I give you, you can get the shape of it and you can determine whether the shape is a polar shape or not. And so if you had AX, this was AX3, but if I had AX3E, then there's 4 things attached. That's tetrahedral. Now I would have a lone pair in one of the positions from this, and I would have X atoms in each one of these. So this is polar because all 4 of those things are not the same. If it had been E2, it would still be the same. It would still be polar. AX2E2 would also be polar. What if I did AX3E2? Well, let's go to the shape. Let's go AX2E3. 3 and 2 is 5. That's a trigonal bipyramid shape. And the lone pairs will go in the equatorial plane first because there's more space. There's 120-degree angles here. Put lone pairs at either of the axial positions, it's 90 degrees to the others. So the lone pairs, all 3 of them are going to go in this plane. Now, if I'm looking at this, the A in the middle, and here, now you can see that this bond and this one are the same. They cancel each other out, and all 3 of these are the same. So this one is not polar. And so forth. You can do the rest of them for yourself and go back and review that segment in the PowerPoints if you need to for all the other possible shapes. The other thing you need to know how to do is how to get the shape of the molecule or ion that you're given. Now, if you want to use my method, it's not mine, but the one I teach in class, you can take the total number of valence electrons, divide by 8, and that's going to give you the number that is attached to E. That would be, like here was a 3, so that's AX3. Here, when I divided, I got 2. So this one was an AX2 type. So in any of these, you can tell whether you've got a polar molecule or not by doing the math method. If you weren't taught that and you're comfortable with the way you learned it last semester with your other professor, then however you get it doesn't really matter. It's just that you get the correct VSEPR shape. And then you can tell whether it's symmetrical or not. If the parts of it are symmetrical, that part is not, it doesn't contribute anything to the polarity. Now, these 4 things are not symmetrical. There's 3 of them that are X atoms, and 1 is a pair of electrons. So those all 4 are not the same. So it's not going to be polar. But in the trigonal bipyramids, you've got a linear part, this part here, and you've got this equatorial part. So this linear axial part is the same on each end, so it's not polar. And all 3 of these axial positions are the same, so it's not polar. So this one, we can switch to some other variations, but really it's just a matter of doing the same thing we did to this one. Now, number 5, we can work it out just by looking at the phase diagram. And it said which of the numbered arrows is called freezing. So if I'm going to, I guess I can do it on the bottom of this one. So I'll just sketch here what the phase diagram is looking like and where all the little arrows are and all this kind of stuff. And we had a 4 that was an arrow in this direction. We have a 3 that is in here somewhere. We have a 2 that is coming down like that. and we've got a 1 that's going this way. Okay, this is solid, this is liquid, and this is gas. So if I want melting or freezing, as this says, I have to go from the liquid phase to the solid phase. That would be freezing. And that's going to be number 4. And that is the correct answer. It's A on the this one. Now, if we wanted to look at other possible ones, so this is the correct answer to this problem. If I'm looking at number 3, this is going from the liquid into the vapor. So that would be boiling at some temperature. If I go from the solid into the gas, that's called sublimation. And if I go from the gas to the solid, that's called condensation. So there's not much else that I could do with that one, but what you've seen here. All right, moving right along. We want to know which solid is miscible with water. Now, despite this being a specific example that I told you about in class, when we talked about what miscibility meant, but what we're looking for in this particular problem is something that matches water. In this case, the solvent is water, given in the problem. And water, it's a bent molecule. There's a hydrogen here, a hydrogen here, and there's a lone pair here and another lone pair on the oxygen like that. So water is shaped like this. It has hydrogen bound to oxygen. So if hydrogen is bound to oxygen, or hydrogen is bonded to nitrogen, or hydrogen is bonded to fluorine, all of these are hydrogen bridged. So they're hydrogen bridged. And so we're looking at a solid that has to be hydrogen bridged. So it's hydrogen bridging because that's in water. This water molecule is bent, and it would be an AX2E2. All 4 things attached to the oxygen atom are not the same, so it's polar. So it's hydrogen bridged and polar, and the London dispersion force for this molecule is low because it has a low molecular weight. It has a compact structure. Compact structure, we're talking about, you've got the mass in that volume, or you could have a strung out molecule with the same molecular weight. But you see, when this thing tumbles in the liquid, it's going to sweep out more area, occupy a bigger volume than this one does. So this one would be low, and this one would be high. I'm trying to think of all the possibilities that you might have to deal with if you're talking about molecules like this. So let's go back and see what examples we have to look at. And now we've got AgOH. Now this is an ionic solid, and it's a hydroxide. So solubility rule says not soluble. You might want to review those from Gen Chem 1. If I've got CH3OH, already this looks a lot like water. I mean, the only difference is if I took the water molecule like this, go ahead and put my hydrogen right there, put this group on, that would be another CH3, have a hydrogen here and here and here, a lone pair and a lone pair. So now, if I'm looking at this molecule, it's a low molecular weight, so it matches low It is polar because if I'm looking around the oxygen atom, the four things attached to the oxygen are not the same, so it is polar. And it does have an oxygen-hydrogen bond, which gives it hydrogen bridging. So this one, it has all of the characteristics that water has. So this one have to be miscible, and it really is. We can reject the other, NaOH. Again, it is a soluble hydroxide by the solubility rules, but remember, no ionic compound is ever miscible with water. It's always going to saturate, and this one will too. It is soluble. It would be the probably best second choice in this, but it's not going to be correct. And the last one is again, look at the oxygens, and I attach two methyl groups, a CH3 on this side and a CH3 on this side. Then this carbon here was a hydrogen here, and a hydrogen here, and a hydrogen here. Now let's stop the share so you can see what I'm doing a little bit better. You can see that this one now, it's a relatively low molecular weight, but it's a bit higher than water, certainly. It is slightly polar because the oxygen atom doesn't have all four things attached to it, so it is polar. But it's not hydrogen bridged. Now why? Because the hydrogens, every single one of them are attached to carbon. There are none of them that's attached to oxygen, nitrogen, or fluorine. So it's not hydrogen bridged. That right there is what rejects this one. So it's not going to be soluble in water, certainly not soluble to any extent. And it's not going to be, certainly not going to be miscible with water. Now, I want to stop for just a moment. And okay, we're ready now for number 7. So let's take a look at that one. Okay, again, this one has to do with London forces and the boiling points and so forth of these. Already see a problem with it that I should have caught before now. We're looking at H2O, H2S, H2SE, and H2TE. Now, if we're just talking about London force, the highest London dispersion force, this was A and B, C, and D. If we're looking at the London force, all of them has London dispersion. Let's stop the share and look at our page. So they all have London dispersion. This is the largest molecular weight, heaviest molecule, largest molecule. So this is the largest dipole London dispersion. Now, and this one, water, of course, would be the smallest London dispersion. It would increase going down as we go there. All of these are polar. because they all have a shape like hydrogen to oxygen, hydrogen to sulfur, hydrogen to selenium, hydrogen to tellurium. Now, oxygen is the most electronegative of the bunch, so water is also going to be the one with the largest dipole forces. So London dispersion is going to the London dispersion is going to increase going down like this, but the dipole is going to increase going up like that. Now, the only one in the bunch, this one, that has is the only one that has hydrogen bridging. So if I'm looking at that, the one with the largest intermolecular force is going to be this one. Hydrogen bridging wins over anything else if it's present at all. So this one is going to have the highest intermolecular force. It's going to be due to water. So that's what's wrong with the answers I see. I think they got changed to maybe alter this, but D is not the highest boiling point. That's going to be A. So I'm going to modify that on here to read correctly. I got to go up one. And this needs to be A. No. A. Now, so this would be the correct answer. Now, D would have the highest London dispersion force. So D has the largest London dispersion, and I think I screwed up when I made this out, but certainly it has the highest London dispersion. The dipole forces in A are stronger than that in any of the others. That's true. All four exhibit London dispersion. That's also true. But the one with the highest boiling point would have the highest intermolecular force, and that would be water, because water is the only one that's hydrogen bridge. So my apologies for that, and I'll try to fix it online. Okay. Moving right along. Which of the compounds A, B, C, D, and that's the ones up there in that other question, had the highest vapor pressure? Now, if you look at the answer, vapor pressure, remember, goes opposite to intermolecular force. So the one with the lowest vapor pressure is going to be the one with the highest intermolecular force. That's going to be this one. Now, as you go to the others, their polarity doesn't change all that much, but their London dispersion force goes up significantly. So the vapor pressure of water is going to be the smallest. The vapor pressure of H2S would be next, and H2SE next, and H2TE next, last. Now remember, vapor pressure goes opposite to intermolecular force. So you have to first look at that, and then you can tell. Okay? So let's go on to the next one. Which of the following represents, these dots represent a hydrogen bridge? The complete Lewis dot structure is not shown, but what you do need to understand is that when you have a line between two atoms, that is the covalent bond between the two atoms. The dotted line represents the hydrogen bridge if it's possible. So if I'm looking at the A, it does have hydrogen bound to oxygen. The lone pair on oxygen, though, is associated with this hydrogen, and that hydrogen is not bound to oxygen. So this is not a hydrogen bridge here. Probably a dipole-dipole type interaction is okay. Now, if I look at this one, I can see the hydrogen is bound to oxygen, and it's associated with a pair of electrons on another atom. That is the definition of a hydrogen bridge. So that one is correct. This one is not. Again, it does not have, it has hydrogen bound to oxygen, but it's associated with another hydrogen, not a pair of electrons. So that's not a hydrogen bridge. This one has hydrogen bound covalently to oxygen, and the lone pair on oxygen is associated with a lone pair on the sulfur. That's not a hydrogen bridge either. So the correct one is B. And I can't think of many other ways to ask that one. Now we're just talking in general terms about a phase diagram. So let's just describe it from memory. Above the critical temperature and pressure, the substance is a liquid. Well, not really, because if you're talking about the critical temperature and pressure, that's the end point of the line that separates the liquid phase from the gas phase. When you get above the critical temperature and critical pressure, you reach a region we call the supercritical fluid region. It is not a liquid region, not a gaseous region. It has the properties of both. So that is not true. Now let's see if this one is true. Below the triple point, temperature and pressure, the substance is a solid. So if you remember, the triple point is where all three of the lines join to each other. So if you're below the triple point temperature, which means you're over to its left, and below the triple point pressure, okay, that's going to probably be in the solid region of the sample. Certainly not the liquid region. It's went all the way from that one. So this is a solid. That would make sense. The normal boiling point always falls between the triple point and the critical point temperature. So the boiling point temperature falls between the triple point and the critical point. That is true. Yes. The more dense of the two phases can be determined by inspecting the phase diagram. That is true. You can look at the slope of that line joining the solid to the liquid. If it slopes to the left, goes top left, comes down to the right, it's sloping downward, it's called negative slope, then that one, the solid will be less dense. But if it's sloped the other way, the liquid will be. You can always tell which phase is more dense, because if you compress something, it will tend to go to the more dense phase. So if you're looking at the phase diagram, so if I'm looking at my phase diagram, and now I'm thinking about having this solid, liquid, gas, and if I imagine I'm somewhere in the liquid region and holding the temperature constant and increasing the pressure, what do? I go into the solid phase. So the solid is more dense in that case than the liquid. If this line slopes the other way, and then I imagine I'm in the, say I'm in the solid region, down here somewhere, low temperature pressure, and I start raising the temperature, you see, I'm going to go from the solid phase into the liquid phase. In this case, the liquid would be the one that would be more dense, and the solid would float. So you can tell which one is more dense just by looking at the slope of this line in the phase diagram. If it slopes like this, then the solid will be more dense. If it slopes like this, the liquid will be more dense. Moving right along. All right, now let's look at these. We're looking at um, different kinds of molecules. And the first thing I want to look for is, are any of them hydrogen bridged? And if you look at all of these, this hydrogen is attached to that oxygen is attached to that carbon, and that hydrogen is attached to that carbon. But I do have oxygen attached to nitrogen, oxygen attached to hydrogen. These two hydrogens are also attached to nitrogen. That hydrogen is attached to oxygen, and that one's attached to nitrogen. So all of them are hydrogen bridged. So the next thing would be the London force. None of them are very polar, so we can just forget about polarity. But London force, if I look at these, let's see, CH3OH, CH32, CHOH. Okay, that's A. I'll pull these over in a minute for you to look at them. B is CH3, CH2, CH2, OH. Okay, that's the shape of that one. C is, they've got a carbon here, we've got a hydrogen here, we've got two CH3s, so C, H, 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 C, H, H, H. And then this carbon is attached to a nitrogen as a lone pair, and two hydrogens attached to it. Okay, that's C. And now we're looking at D, is nitrogen has a hydrogen attached to it, and then it has a lone pair, and it has two CH3s. So now we're looking at the molecular weight and so forth. So okay, so let's see. 12 and 3 would be 15. And this one's got two of them, times 2, plus another 12, plus a 16, and two hydrogen, plus two more. And this one looks like it's got a molecular weight of 60. This one is 15 for the CH3, plus 14 for the CH2, plus another 14, plus a 16, plus a 1. This one's 60 also. And then this one, 2 is CH3, so that's 15, and there's two of them. That's these two CH3s, plus another 12, plus a 1, plus 14, plus 2. That's 59. And that one is going to be, this is CH3 for two places. That's a 15 and 15. So it's 15 plus 15 for the two CH3s, plus 14 for the nitrogen, plus 1 for the hydrogen. That one's 45. Okay, and what did I get for this one? I don't know. Let's do it again. No, I did it. Right there it is. Is that right? 15 times 2 plus 12 1's 13 plus 14 16. Let's see. Yeah, it's 59. So I'm right. Now, you can see that all three of these have about the same mass. This one is smaller. So this one is going to be the lowest of the London forces. So it's going to have the lowest intermolecular force. Let's stop the share so you can see the screen a little better. Now these three we said are about the same. So of these, which one would be highest? Well, since they all have about the same molecular weight, this one I'm saying is all strung out. So I'm going to say that this one's going to have the highest. And then this one, let's see, the number of atoms in this one, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It would be 12 atoms in this one. What do we got in this one? 4 times 2 is 8, 9, 10, 11, 12. We got 12 in that one. So it appears to me that hydrogen bridging is going to be a little better in this one. So if I'm having to choose, I'm going to say that A is greater than C. So if I'm listing them from lowest value to highest, it would be D lowest. Then after D would be this one. That would be C. And then I would go to A, and then I would go to B. Now this is in intermolecular force. Okay, so it looks like that's my best answer anyhow. So let's see what we've got. So vapor pressure, P vape, if the IMF goes up, well, I've got them like lowest to highest, right? Yeah. So if IMF is going down the way I've got them listed here, vapor pressure should go up. So the one with the lowest IMF should have the highest vapor pressure. So the highest vapor pressure, then we're going to argue that it's either B or C. Now I'm going to go to the other extreme. Which one would be the smallest? Well, the smallest one would be then B, because that's got the highest intermolecular force, so lowest vapor pressure would be B. So I'm going to take this line of reasoning here, which would be D less than A less than C less than B. And, you know, the two in the middle, it's just I hesitated quite a bit in trying to decide which of these was better, and it could go either way. But these two should be correct. Highest and lowest should be correct. And so that's what we've got for that one. And then which is one has for decreasing surface tension? Well, again, the surface tension now goes in the opposite direction. So if the IMF decreases, if it decreases, then the surface tension is also going to decrease. So it should just reverse what we did up there. So if we went back to this one, we should be listing B, C, A, D. It would go the opposite. These two should go opposite each other. All right. Okay. Now, number 13, if we look at that, we can see we're given a solubility in pounds per liter of water, 0 degrees in 1 atmosphere. We look at the volume of the Earth's ocean, the partial pressure of 240 times 2.4 times 10 negative 4 atmospheres. What mass of CO2 is dissolved in the oceans? Okay, so if we stop, wait a minute, I need to stop the share. And now let's go over here. I just stopped it too quick. I need the data. So number 13, the solubility is equal to 2.3 times 10 to the negative 3 pounds per liter at 0 degrees C would be 273 degrees K and 1 atmosphere pressure. Okay, and it says the volume of the ocean is 1.2 times 10 to the 21 liters, and the partial pressure of CO2 is equal to 2.4 times 10 minus 4. This is in atmospheres. Okay, that's what we got up there. So the solubility by Henry's law is some constant times the pressure. So I can get the solubility this way. The constant is going to be the same. It's going to be equal to solubility, 2.3 times 10 negative 3 pounds per liter divided by the pressure, 1 atmosphere. So the solubility is equal to this constant. It's 2.3 times 10 minus 3 pounds per liter per atmosphere times a P. So now all I have to do is plug in the pressure and plug in the volume, and I've got it made. So the solubility of CO2 in the ocean is 2.3 times 10 minus 3 pounds per liter per atmosphere. The pressure is 2.4 times 10 to the minus 4 atmospheres. So my atmospheres are canceling. And then multiply by the volume in the container, and the volume is 1.2 times 10 to the 21 liters. And now my liters will cancel. So I've just got to do the math. 2.3 times 10 minus 3. And I'm going to multiply that by 2.4. Exponent is minus 4. And multiply that by 1.2. Exponent is 21. Okay. So I got 6.62 times 10 to the 14th pounds. So that is a bunch. And you can see from the answers that is the correct answer. Then, and this was the math that we did. We took the solubility at given temperature and pressure that allowed us to calculate the constant in the Henry's law relationship. So I solve for the constant, put the value of the constant in here, times the pressure times the volume. So there's my constant times the pressure in atmospheres times the volume of the ocean, and do the math, and we got the answer. All right, and moving right along. What is the molality of HCl in a solution containing 150 grams of water mixed with 10 grams of hydrochloric acid? So number 14. And we want molality. Now, in doing these problems, if molality is being asked for, you have to be able to get the number of moles of the solute and divide it by the number of kilograms of solvent, in this case is water. So I need to get these two numbers and divide them out. Okay, so let's go plug in the data. And the data we're given is 150 grams of water. And we are given 10 grams of HCl. And molecular weight here is 18. Molecular weight here is 36 and a half. I've got all the data over here now that we've had. If I make that a little bigger for you, then we can work the problem. So the number of moles is going to be the mass of the solute divided by its molecular weight. So we got 10 grams divided by 36.5, and that's going to give me number of moles. Number of kilograms of water, we had 150 grams, and we need to divide that by 1,000. That's 1,000 grams in a kilogram. So we can do that math. Now, we could just enter this directly in the calculator the way it is, or you could rearrange it. This will come out as 10 times 1,000 divided by 150 and divided by 36.5. If it's the outsides times each other divided by the insides times each other. That's the way you reduce a complex fraction. So if I want to do the math, I can clear that out and say 10 times 1,000 divided by 150 and divided by 36.5. And I get 1.8264 molal. So if we now go back and look at the screen, we should be able to get the answer. 1.826 would be 1.83. That's good. Now, I don't need to reiterate how you could work that problem because we're going to do others just like it with the other concentration units. Number 15, what is the molarity M? And once you see that, you know that you must be able to take the number of moles of the solute and divide by the number of liters of the solution. Okay, now let's see what we're given. The solution is 30.0% HNO3, and it has a density of 1.180 grams per milliliter. Okay, now here's one where I'm given a choice of what to divide by what. Well, I want to divide by 1. So I have 1 liter of the solution. That's equal to 1,000 milliliters. And now if I look at the density, if I multiply from the density, the mass of the solution is going to be 1.180 times 1,000. And I've got that many grams of the solution in 1 liter. Well, that's 1,180 grams. But the solution is, I need moles of solute. So I need how much solute is in there, but I'm given the percentage. So it's 0.300 grams of HNO3 per 1 gram. I could have put 30 and 100, same thing, of the solution. So now, if I multiply this out, what I'm going to have, 1180 times 0.300. Now that's grams of nitric acid. I want to find out how many moles is that, because that's what has to go in the numerator up here. So the molecular weight was probably given in the problem. Let's see if it was. Save me having to calculate it. Yes, 63.02. So I want to divide by 63.02 grams for 1 mole for nitric acid. So now let's do the math. So I can take 1180 times 0.3 divide by 63.02. That gives me 5.617. We've got that many moles, so the molarity is going to be that many moles divided by the number of liters, 1 liter. So it's 5.617 moles per liter. There we go, 5.62 is the correct answer. All right. Right, we're ready for number 16. It's going to take a long time. We're halfway mark, but I wanted to take the time to carefully explain things with you as we went along. Okay, we're given the vapor pressure of water at some temperature is 17.5 torr, and we're given urea, that is a non-volatile compound that is soluble in water. We want to know what the vapor pressure of water over a mixture containing 50 grams of water mixed with 50 grams of urea at that same temperature. All right, the relationship is Reynolds law. P is equal to the pressure due to the water. That's the only thing that's got a pressure. It's going to be the mole fraction of the water times the vapor pressure of the pure water. So all we got to do now is do our math. And we've got 50 grams of each. All right, we got the data. Now let's work the problem. Oh, wait. This vapor pressure of pure water, we're told, is 17.5 torr. All right, so let's plug in the numbers. So the vapor pressure of water over this solution is going to be the mole fraction of water. Okay, that's going to be the moles of water divided by the moles of water plus the moles of the other compound. I just CMPD here. Okay. Now, let's see. The molecular weight of the compound is it's 60.06. And of course, molecular weight of water is 18. Doesn't say, but 18.02 is correct. Okay, so let's stop the share and work the problem. So here's my data. So to get the number of moles of water, I take the grams of water. The grams of water is 50. I want to divide that by the molecular weight of water is 18.02. All right, now that gives me the moles of water. I need that same down here. So it's 50 divided by 18.02 plus the moles of the salt is going to be 50 divided by 60.06. Okay, now there is my data, and I got to multiply that now by the 17.5 torr. Okay, I'm going to show you a trick on doing this calculation. Let's first calculate 50 divided by 18. So let's clear my screen. 50 divided by 18.02. And now I'm going to push equal. Now that gives me the number of moles of water is 2.7746. So what I'm going to do now is I'm going to say divide. And what it did is it copied the previous answer. I want to divide by a left parenthesis, and I want to divide by my second answer, and plus 50 divided by 60.06, close the parenthesis. Now what I have on my screen is this, so all I got to do is multiply that by 17.5. And now I have the answer. The pressure should be 13.461 torr. Let's see if we did everything correctly. 13.5 torr. There we are. Now we're ready to do number 17. What is the molar mass of an unknown if 0.0216 grams in 3.24 grams of benzene? There's the data for benzene. Forms a solution that freezes at 5.206. So now this is a freezing point depression problem. So I'm going to say delta T for freezing is I, but this is not an ionic compound, so I is 1. It's K sub F times the molal concentration. Okay, so this is my relationship. Let's put in what we know. It freezes at 5.206, and the freezing point is 5.455. So delta T is 5.455 minus the smaller number, 5.206. That's my delta T. That's equal to K sub F. K sub F from the data is 5.065 degrees C per molal times M. Now, I want to show you when you're doing a problem, you get the relationship you need, plug in what you know, and solve for what you don't know. Well, the molal concentration I can solve. Molal concentration is going to be this difference divided by 5.06. So let's do that. So it's 5.455 minus 5.206. Okay, so it's 0.249. I need to divide that by 5.065. Divide by 5.065. All right, looks like that. Okay. Now, I'm told that the molal concentration is 0.04916 and some other digits molal. Now, is that the answer? No. We're looking for molecular weight, and molal is not. So we've got to say, okay, well, what's molal equal to? It's the number of moles of the solute divided by the number of kilograms of the solvent. Okay, we know that number. If we go back, we can get it. Okay, we know we put 3.024 grams of benzene grams. So if I want to know the number of kilograms, the number of kilograms is that divided by 1,000. So the number of moles is going to be this number, 3.024 divided by 1,000. And then it's times 0.04. And now this is going to be number of moles. Okay, so let's do the math. I still got this number on my screen, right there. I want to multiply it by 3.024. And I want to divide it by 1,000. Okay. Nope. Let's back this up. This is not looking right. I want to take that. I want to do times. Why didn't answer come up? I'm going to put it in there anyhow. I'm going to put second answer times 3.024 divided by 1,000. Okay, so that should be right. And what I get is the number of moles. Let's go back where you can see what I'm doing. Okay, so I did this math. I took the difference divided by that and got this number. And I said that's the molal. It's number of moles over number of kilograms. I know I had that many grams of benzene divided by 1,000. That's the number of kilograms. This goes here. So to solve for number of moles, I need to multiply that by the 3.024 times 1,000 times what I got up here. And now I've come up with the number of moles is 1.4866 times 10 to the minus 4 moles. Now, how do I get number of moles? I'm going to take the grams and divide by the molecular weight. Now, I do know what the number of grams is from the problem. Let's go back and look at it again so we can put this number in. We had 0.0216 grams. So I'm looking at that, to solve for this, I need to take that number and divide by my answer that I have on here. So I want to go here, and I want to take that number is in my answer. So I want to take 0.0216 and divide by that answer that I got up there, and I get 145.29. .295 grams. Okay, now, and the correct answer we get is 145 grams per mole, which is what we got. Now, the next one, we can talk our way through it, I think. If we look at this compound, it says, what is the Van 't Hoff I factor for nickel 3 hexachloronickelate 2? And you don't have a clue what that means. And I understand that. It wasn't meant to. But if you look at the way its formula is written, you look at the way the formula is written, you've got Ni4, and then we've got that attached to NiCl6,3. So if I look at this, I've got 4 cations and 3 anions. 4 plus 3 equals 7. So the Van 't Hoff I factor would be a 7 for this molecule. So there's 4 cations and 3 anions. 4 and 3 is 7. Number 19. A substance melts below 200. Okay, so that's a fairly low melting point. I guess I haven't eliminated anything except covalent networks. It couldn't be that because their melting points are thousands of degrees. So it couldn't be this one. I can eliminate it now. It's not an electrical conductor in the melt or the solid. Well, that certainly eliminates if it doesn't conduct a current in the melt or the solid, it's not metallic. So it can't be that one. If it were a non-conductor in the solid, but a conductor in the melt, it would probably be ionic. So the only one left is molecular. Molecular compounds typically do have low melting points. They're not conductors in any state. And so this could be written several different ways, but of these choices, you can see that metallic things will always conduct electric current either in the solid or the melt. Ionic compounds will conduct in the melt, but not the solid. Covalent networks, some of them do conduct an electric current in the solid, but not the melt. But covalent networks are going to have very high melting points. And then molecular compounds are going to be described like this one is. So you could have several different examples, but they would be still the same. Now, we've already answered number 20. It was, again, a question about a body-centered cubic crystal. And if you remember, the body-centered cubic has one in the corner. All of them have that one particle, one corner particle, but the body-centered has one in the center as well. So 2 is the correct answer for this one that we've already done. Now, number 21 is an osmotic pressure problem. 21 it is. And the equation is pi equals molarity times R times T. So we're asked to calculate the molarity. And we've got 500 milliliters. We put 25 grams of glucose. The molecular molarity is the number of moles divided by the number of liters. And we had 25 grams of glucose. Molecular weight is 180.2. And we put that in a 500 milliliters is equal to volume. Okay, so let's plug in the numbers and solve for it. The molarity is number of moles. Well, it's 25 grams. That you see what I'm doing. 25 grams divided by the molecular weight is 180.2. And I want to divide now also by the volume, and that's 500 milliliters. You could write that if you want to. 500 milli is 10 to the minus 3 liters. This is going to be moles now per liter. That's the correct unit. So there is my molarity. R, we have to know for ideal gases and for this equation, R is 0.0821 liter times atmospheres over moles and Kelvin temperature. And the temperature, I didn't copy it, but I think it was 25 degrees. Yes, it was. It was 25 degrees. Okay. And so the temperature was 25 plus 273.15 if I want to put it in. So now, pi, osmotic pressure, is number of moles is 25 divided by 180 and 500 times 10 minus 3 times the temperature is 25 plus 273.15. And what I'm going to do is I'm going to work out this first. So if I clear the, I take 25 plus 273.15 and I'll push equal. Now that did that. Now I need to multiply that by 25. I need to divide it by 180 and divide it by 500 exponent minus 3. So that should be it. My number is looking pretty big, 82.81. I'm a little suspicious of that number. Let's go look and see. I need to share screen so you can look at it with me. Yeah, that's what I thought. Something's wrong. 25 grams, okay, divided by 180, the molecular weight, 180.2, and the volume it's in is a 500 milliliter flask. Well, let's do my numbers again. 25 times, no, back it up. Maybe that's the mistake I made a while ago. 25 divided by 180.2 and divided by 500 exponent minus 3.277. So that, and then I multiply that times the left parenthesis 25 plus 273.15, right, equals, I'm still getting 82.17. Okay. Let's try again. 25, clear. Okay. I'm still getting 82. So the only thing I can see is this answer has to be wrong. I don't want to waste any more time on it, but I've worked it 3 times and I think I'm doing it right. At 25 grams, I divided it by 180. That's a number of moles. Oh, I haven't multiplied by the value of R. That's what's wrong. Okay, so um, there's my mistake. I forgot to multiply it by R. So if I say times 0.0821, so let's take that number times 0.0821. Yeah, that looks a little better. That gives me a number that made sense, 6.799 atmospheres. Yeah, there we go. And that is the correct answer. Okay, so we're good. 22. Vapor pressure of benzene is this value at 20 degrees C and 75 torr. When 25 grams of camphor added to 100 grams of benzene, the vapor pressure of benzene is 65. What is the molar mass of camphor? Okay, so I maybe be able to work that here. 22. Okay, P of benzene, the pure benzene, has a vapor pressure of 75 torr. And what else have we got? You got 25 grams of camphor. I'll just write it like that. And 100 grams of benzene. Okay. Vapor pressure. P of the solution is equal to 66.5 torr. All right, so let's stop the share and then let's solve the problem. Okay, so here are our data. Now, the vapor pressure of the solution is going to be the mole fraction of benzene times the vapor pressure of pure benzene. Okay, there is a relationship. Plug in what we know. Vapor pressure solution is 66.5 torr. That's equal to the vapor pressure of the benzene is 75 torr, and times the mole fraction of the benzene. We plugged in what we know, we solve for what we don't know. Mole fraction of benzene is going to be equal to this number divided by this number, 66.5 divided by 75.0. So let's do it. Okay. It's 0.88666. repeating sixes. Now, what is mole fraction of benzene? Mole fraction of benzene is going to be the moles of benzene. Well, we put 100 grams of benzene. So its number of moles is 100 divided by the molecular weight. Okay, so let's go back and see what we were told the molecular weight of benzene is, 78.1. And now that's going to be divided by 100 divided by 78.1 plus the moles of camphor. Okay, so there we go. Now I've got this number, remember. Get another piece of paper and continue. Okay, so let's stop the share so we can so you can see what we're doing. So what we've done is we're given the pressure of the pure benzene, the number of grams of camphor, number of gallons of benzene, the pressure of the solution. So this is a relationship, Raoult's law, pressure of the solution, mole fraction of benzene times the vapor pressure of benzene. The pressure of the solution was 66.5. The pressure of pure benzene is 75, so I can solve for that mole fraction by taking this and dividing by this, I get this number. So the mole fraction of benzene is 0.886 divided by these numbers. So I'm going to put this down here, and then we're going to do a little. So the mole fraction of benzene is 0.88666. Now this is my answer from the previous calculation. And I want to multiply that by this, which would be 100 divided by 78.1 plus the moles of my camphor that I don't know. And that's equal to 100 divided by 78.1. Now I wrote it this way for a purpose. Let's do a little algebra. I'm going to take this times this. So it's 0.88666 times 100 over 78.1. I'm going to bring this one over here now. Minus 100 divided by 78.1 plus 0.8866x equals 0. Now, that's the algebra. I subtracted this from both sides. I got this. All right. So let's do this, all of this math now and see what we have, and then we'll solve for x. So we've got this number, which is on my screen. I'm going to multiply times 100 divided by 78.1. And then I'm going to subtract 100 divided by 78.1. So what I come up with when I do this is minus 1.280 and some other digits, plus 0.866x equals 0. So I'm going to add this to both sides. So what I'll wind up with is if I add plus 1.280 to both sides, I wind up with 0.866x equals 1.280. So x is going to be 1.280 1.280 divided by 0.8866. Okay, 0.88666. No. Back it up. 1.280 divided by 0.86688. There we go. So X is 1.4436. And what is that? That's moles. How do you get the number of moles? Well, you take the grams, divide by molecular weight, and that's got an equal number of moles, 1.4436. And the number of grams that we started out with was of the compound. I didn't write it down. Okay, when 25 grams of camphor, so the grams is 25. That's not right. I made a mistake. Oh my goodness, this is a bad one to make a mistake in. Divided by molecular weight is equal to 1.4436. Okay, molecular weight is 25 divided by that number. So I know it's wrong, but I'll do it. 25 divided by that. Answer is 17.3. No. So I made a mistake somewhere. Where? Okay, let's back up and look. The mole fraction of the solution was 66.5 torr. Mole fraction of the pressure of benzene was 20. So 66.5 divided by 75. 0.88666. Okay, so I think that's good. Now, that's equal to the number of moles of benzene is 100 divided by 78, right? 100 divided by 78.1. So let's do 100 divided by 78.1. Okay, so I'm going to another piece of paper. I'll let you watch me try to get the egg off my face. Okay, here we go. All right, I've checked that number looks good. And so the mole fraction of benzene is 0.8866. Now, the moles of benzene is equal to the weight is 100 divided by 78.1. 100 divided by 78.1 is 1.2804. I'm just going to run the numbers through this time. So the mole fraction of benzene is 0.8866 is equal to, now, the moles of benzene is 1.2804 divided by 1.2804 plus X, that's going to be the moles of the compound. Okay, so let's cross multiply. So 0.88667 times 1.2804 plus 0.88667 X. So I've cross multiplied, I multiplied this thing and distributed with that, and that has to equal to 1.2804. Okay, let's do the math. 1.2804 is equal to this number times this one times 0.88667. That's 1.1353, a bunch of other digits, plus 0.88667x. So I want to now subtract this from both sides. 1.284 minus this number. I get 0.1451, 0 more digits, is equal to 0.8867x. Now, does that look right? Okay, so X now is going to be this number divided by 0.8867. So divided by 0.8866. There we go. And I get 0.16365. Okay. And that's equal to the number of moles, which is the grams, divided by molecular weight. And molecular weight is equal to the grams, and the number of grams we dissolved was, what did I say way back up there? I think it was 50 grams, but let's go look. And 100 grams of benzene, so I had 100 grams of benzene divided by 0.16365. So 100 divided by that answer, and that's not right either. Okay. Now I've got double egg on my face. Well, I can't see where the mistake is. Let's go back and try one more time, and then I'm going to give up and work it at my leisure and fix it on D2L if it's wrong. Okay, so let's look back again and see what we had. We had vapor pressure 66, 75. 66 divided by 75 is, I've done that 3 times. I know that's right. 0.8866. Now, the number of moles of benzene was 100 divided by 78. So we're going to, instead of doing it this way, we're going to do this. Now there's that 100 grams. Oh, that's what's wrong. It wasn't 100 grams of benzene. I needed 100 grams of camphor. I needed the grams of camphor. There we go. There's our problem. Instead of that being 100, grams of camphor was 25. So if I take, let's take 25 and divide by 0.16365. Okay, I get 152. Okay, well, it really isn't that hard a problem, 152.8. And if we look at our answer, it's 153, so we're okay. There's plenty of opportunities to make stupid mistakes, and don't feel bad if you make one. I make one every once in a while. Oh, actually, that was the first one mistake I've ever made in my life. And that was the first lie I've ever told in my life. And that was the second one. And that was the third one. But the point is, it is possible to make a mistake. And if I were taking this exam and I did that, I would have worked it once. When I didn't get the answer, I would put a note, come back. And if I didn't get back working it out, I would make a guess. Okay. I wouldn't waste as much time as I did with you. All right, 23. Let's finish. What is the percent of HCl given weight in a solution that is 5.43 molal? All right, what is percent? It's the mass of the solute. I don't want to write with that pen because you can't read it. Percent is the mass of the solute divided by the total mass and multiplied by 100 to get percentage. Now, we're given a solution that is molal. What is molal? Molal is the number of moles divided by solute divided by the number of kilograms of the solvent. Okay, now, we've got to get this number, so I've got to put this number together so that I can get the data that I want. Here's what I'm going to do. I'm going to say I have 1 kilogram of solvent. That's, of course, 1,000 grams. The molal, I know, it's 5.45. Let's make this so you can see it a little bigger. Okay, so the number of moles of solute is going to be equal to 5.45 moles. And the number of kilograms of solvent, that's going to be equal to 1 kilograms, or it's 1,000 grams if I need it. Okay, so now I'm going to go up here and I need the number of moles. Well, I've got, I need the mass of the solute. Well, I know the moles, 5.45 moles of the solute. The solute was hydrochloric acid, I think. Yes, was hydrochloric acid. So 5.45 moles, hydrochloric acid is 36.445. .53 grams per mole. So this is going to give me the mass of the HCl in this solution. So it's 5.45 times 36.53. And that's 199.0885. Let's make this bigger again so you can see it. And so I've got, for my percent, I've got the mass of the solute, 199.0885, and that's grams of solute. The total number of grams is going to be that plus 1,000. So it's that number divided by 199.08 plus 1,000 grams total times 100. So I've got this number on my screen. I want to divide by left. Second answer plus 1,000. And I get that, and then I multiply it by 100%. So I'm coming up with 16.6%, it looks like. All right, let's see if we got that one okay. 16.6 is correct. All right, that's number 24. All right, so number 24. The density of a 3.48 molar solution of HCl is 1.06 grams per liter. What is the percent HCl in this solution if the molar mass of HCl 36.53 and the molar mass of water is this? So what is the percentage? Again, that's going to be equal to the mass of the solute divided by total mass times 100, and put it into percentages. And so we're told the solution is the molarity of the solution is 3.48 molar, and the density is 1.06 grams per milliliter. Okay. All right. Okay. Now, this is number of moles divided by number of liters. Let's stop the share so you can see the screen, paper a little better. So if I had 1 liter, that would be 1,000 milliliters. And the mass of the total solution, if I multiply by the density, 1.06 grams per milliliter times 1,000 is going to be the total mass then is going to be 106 grams. That's what I'm going to need to go in there. Now, that 1,000 milliliters would have 3.48 moles of HCl. The mass of the HCl would be 3.48 times 36.53 grams per mole. So I'm going to take the 3.48 times 36.53. That gives me the numerator for my percentage is 1.27, 127 rather, 127.1244 grams divided by the total mass of the solution, 1060, and multiplied by 100. So let's do that. So 127.12. Oh, no. I've got that already in my calculator, so I don't need to do that. Okay, I'm going to take that answer, second answer, and I want to divide it by 1060 and multiply it by 100. 11.99 percent. Let's see what we got for an answer up here. 12.0 is the best answer. Okay, 25. What's been HCl in a solution is 0.15 mole fraction. So you see we've done just about all of the different types of conversions that we might want to do. 25. What is the percent of HCl in a solution? Is 0.145 mole fraction HCl. So we want to do percent. So what is the recipe for percent? It's going to be the grams of the solute divided by the total mass, total grams, and then times 100. That means I got to get these data from what was given. I was told the mole fraction. The mole fraction is going to be moles of the HCl divided by the moles of HCl plus the moles of water, salt, that's present. Total number of moles here. Again, what did we want to divide by always if we could? We want to divide by 1, right? So I'm going to assume there's 1 total mole. The mole fraction, should have copied my data. The mole fraction is 0.145. Okay, so 0.145 moles is this. Now, if this is a 1, the moles of HCl is going to be 0.145 moles. The moles of water, total moles is 1, so it's going to be 1 minus 0.145. And let's see, we can get a number for that. 1 minus 0.145 is 0.855. Okay, so now we got the moles of each. So I can get the grams of the solute. The grams of the HCl is going to be 0.145 multiplied by, oh, sorry, you need to see what I'm doing. It's so we know this is the formula we were using. The number of moles of the HCl was 0.145 was the mole fraction, and it's moles of HCl over total moles. Total moles we said equal to 1. So that made the moles of HCl to be equal to the mole fraction 0.145, and the moles of water is 1 minus 0.145, 0.855. So I can get the grams of each. Now the molecular weight of HCl was 36.53, I think I remember, grams. And so the grams of water is going to be 0.855 times the molecular weight of water is 18.02 grams. So I've got all my numbers that I need. 0.145 times 36.53, 5.29. So this number is 5.29685. The moles of water is 0.855 times 18.02. It's 15.4071 if I copy all the digits. So the percentage is going to be the 5.29685 divided by 5.29685 plus 15.071 and then times 100. So here we go. Okay, so I've got the 15 on my screen, and the number above it is the other one that I want. So I'm just going to say, I'm going to take the number that's on my screen, I'm going to add to that 5.29685. I'm going to push equals. So the bottom is 20.70893. I'm going to take the 5.29685, and I want to divide that by the answer that I have now and multiply it by 100. I'm getting 25.58%. So hopefully that's what we've got on the exam. 25.6, that's pretty good. Okay, we're getting closer. What is the mole fraction of solution composed of 50 grams of water and 30 grams of HCl? This is one that's kind of straightforward, plug and chug from the definition. So number 26, mole fraction of HCl is equal to moles of HCl divided by moles HCl plus moles of water. Okay, now we've got 30 grams of HCl, and it's 36.53. We've got 50 grams of H2O, 18. It's 18.02 is molecular weight. So let's stop the share, work the problem. So the mole fraction is going to be 30 divided by 36.53, left parenthesis, 30 divided by 36.53 plus 50 divided by 18.02. Okay, so let's do the math for this one. So 30 divided by 36.53 equals. Now that number is 0.8212 and it's stored in my register. So I wanted to divide that by the left parenthesis, that answer plus 50 divided by 18.02 and close my parenthesis. Now it's important to close that parenthesis. So if I didn't screw up something, it's 0.22838 is the mole fraction. So let's screen share and see if we got it. 0.228. Okay, very good. 27. Now, 27, and it says when calcium chloride, if I take CaCl2 and I dissolve it in water, I make a solution. And I want to know, I'm doing this at 1.5, what is it, 1.6? 1 atmosphere and 25 degrees. The temperature increases. So imagine the experiment. I've got a little beaker. I've got some water in it, got a thermometer in the water. Dump in some calcium chloride, stir it up, and temperature increases. So that means this reaction gave off heat. So heat is over here. Okay, let's do it down here. See, and what we want to know is the effective temperature and pressure. CaCl2 and H2O forms a solution. And it gave off heat, it got hotter, so heat is a product. Now the other possibility, and it would be true for some things, a lot of them, it might get colder and the heat would be on the reactant side. But this is a relationship that we want to look at. This is solid, this is liquid, and the solution is aqueous or liquid. Now, when you look at a relationship like this, now this has to do with some stuff that we would have covered in lecture a little bit. It's not a big deal because what's going to happen when you apply pressure, you already know. If you apply pressure to a gas, the solubility increases, doesn't it? Okay, so if you got a reaction that does not involve gases, pressure has no effect. Now, if you have a gas over here in the reactant, which it isn't, but if you did, when you increase the pressure of a gas, you increase the solubility of the gas. So if there's no gases, pressure has no effect. You can raise the pressure. It doesn't change the solubility. It doesn't make it more or less soluble. It doesn't affect it. But if there's a gas involved, if gas is over being dissolved in water, then adding pressure is going to increase the solubility. It's going to make it more soluble before it reaches saturation. So that's the effect that you can always count on for pressure. If it doesn't involve gases, it has no effect. Now, this isn't the reaction, but suppose all of these were liquids, but a product was a gas. Well, if that's the case, you put pressure on, you're going to shift back the other way. You're going to try to absorb that pressure you're putting on. So if there were a gas in a product, it would make it less soluble if you increase the pressure. If the gas you're dissolving is, if that gas that you're dissolving is a reactant, then pressure will cause its solubility to increase. So pressure we can get rid of easily. How about temperature? Well, what's going to always happen in nature is when you try to do something, the system is going to shift in a way that tries to undo what you've done. It won't undo it totally. This is called Le Chatelier's principle. You can Google that or look it up in the textbook if you want to see what it actually is saying. But the effect is this. When I increase the temperature of the beaker, I'm trying to get it hotter. Well, I'm supplying heat. So if the process is exothermic and heat is already coming off, if I try to put in more, it'll make it less soluble. So if increasing the temperature, if exothermic, it shifts left. And in this case would be less soluble. So from the information we're given in this problem, we believe calcium chloride gives off heat. It's exothermic. Heat is a product. Supplying more heat is going to shift it to this side. And there are many examples where this is true, but there are other examples, like, for example, if you took ammonium chloride, solid, and you put this into solution to make the solution, that gets so cold, it'll frost over the beaker you put it in. So that means when this dissolves, it's sucking heat out of the water to make it do it and make it colder. So you have to supply heat for this solution to take place. So in this case, if you increase the temperature, you would make it more soluble. You're going to put more heat, that's a reactant, it's going to go that way. Whereas if heat had been a product, that's the one in the example, it shifts to the left. So that really covers everything that is on your practice exam. There are 3 other questions on your exam, but they are surprises. They won't be a surprise when you see them, I don't think. There'll be things that I emphasized in lecture, and I think you'll remember it when you see them. So that's all there is to this one. And I know it's been a long video, but I wanted to take the time to go over the entire practice exam with you. Now, the other advice I would give you is it's long. My exams are always long. So don't waste time like I did on problems that you missed. If you have difficulty solving a problem, go on to the next one. Just note on your scratch paper that I need to do number 21 again, or whatever it was. So, and then go on. So again, I would work as quickly as possible. And when you get near the end, and I'll warn you in the classroom when we're close, or I'll have a timer up so you can see. When you're getting within 10 minutes or so, you probably should stop working the problems. If you haven't finished, go back to the ones you skipped already and guess something if you don't know. And then go, when you get to the very end, see if you know how to work the rest of the test. If you don't, just before it ends, work as long as you can, but just before the end, make sure you do have answers to all the questions, and then be sure to get it posted before the deadline. It won't give you another attempt. So don't leave the exam for any reason. Okay? All right. That's enough. And this will end this